Hello, everybody. I'm going to be out today, so I was going to try leaving you some notes here through YouTube. You're going to be working with complex numbers today. In particular, you're going to be looking at complex numbers in polar form. What we know already is that we can write a complex number in rectangular form. And we see something like this where we have a real part, A, and an imaginary part, B, to every complex number. And we know that when we graph these guys, we have two axes. We have the real axis, and we have the imaginary axis. So as an example, we're going to look at the number z is equal to 2 plus 3i, and we wanted to plot that point. We go 2 units on the real axis, and we go 3 units on the imaginary axis, and we put a point. Now that number, z, has a length, which we call the absolute value. In this case, the absolute value for real numbers means nothing more than how far is that number from the origin. So we're going to take advantage of the Pythagorean theorem. We can make a little right triangle out of this guy. So in order to find the absolute value of z, we are going to do the square root of 2 squared plus 3 squared. And we are going to get the square root of 4 plus 9, or radical 13. If it would simplify, we would go ahead and simplify it, but that number does not simplify. Now what's different here in this section that we're working on is we're going to be looking at polar forms. So the polar form of a complex number, we have to think about angles and distances from the origin. So say that we have a number here, a point in the complex plane, and that distance from 0, let's just say it is something called r, where this is theta, and we have the value of a on the imaginary, we have the number a on the real and b on the imaginary. So this number right here, okay, this point represents the number a plus b I in the rectangular coordinate system. However, as a polar point, we're going to think about the triangle that this guy makes. So a is going to be representative of this length because that's the origin to the value a, and b is going to represent this length of the triangle, which is the distance from the x-axis up to the point a plus bi. So in order to relate the angle and this value of r, which we now know is our absolute value from the previous slide, we know that the equation is the cosine of theta is equal to a divided by r. That will lead us to representing a as r times the cosine of theta. We've seen this before. And we also know that the sine of theta would be the b value divided by r, which would lead us to b is equal to r times the sine of theta. So therefore, if we have the complex number a plus bi, we can rewrite this as a polar number, replace a with r cosine of theta, and b with r sine of theta. I'm going to put the I first. And what we can do is factor out that r from both of those terms. And we have r times the cosine theta plus I sine of theta. And that right there is the form that we are going to write complex numbers in when we write them as polar form. So for example, add a page here, I'm going to give you a complex number, -2 minus 2i. Now that right now is in rectangular form. What I want you to try and do is change that to polar. Well, if you think about the graph of this number, negative 2 minus 2i, that's going to be a point down here, right? Because we've gone left 2 and down 2 on the imaginary axis. So what we need to do is we need to determine the r value, and we need to determine the theta value. So if you look at this enough, what you're going to recognize about that angle theta is that that is going to be the angle 5 pi over 4. Because this triangle formed right here is 2 to the left, and it's 2 down, so that's a 45, 45, 90 triangle. So we have left 2, down 2, well, this r value is going to turn out to be 2 radical 2. And this angle is going to be 5 45-degree angles, or 5 pi over 4. So my form is going to be 2 radical 2, because that's the length of r, times the cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. And that's the polar form. So that is having changed rectangular form into polar form, one of the things that you're going to be asked to do. Another thing you're going to be asked to, excuse me, another thing you'd be asked to do is to go the other direction. If we give you a number as a polar form, we want you to be able to change that into rectangular. So an example of that is going to be, if I give you the number, let's say z is equal to 4 times the cosine of 30 degrees, I'll do this in degrees, plus I times the sine of 30 degrees. That's a polar form of a complex number. So what we want to do is change that into rectangular form. Well, what we know about 30 degrees is in quadrant 1. So if we envision the 30, 60, 90 triangle oriented as such, with a 30-degree angle in the standard position, we would use the sides 1, 2, and radical 3. And so what we have here is 4 times the cosine of 30. Well, looking at this triangle, we know that the cosine of 30 is going to be the square root of 3 over 2. And that the sine of 30 is going to be 1 over 2 times I. So if we go ahead and we distribute that 4, what we are going to get is 2 radical 3 plus 2i. And so that is an example of how to take something that is given to you in polar form and change it into rectangular form. Now, one of the reasons we want you to have some experience using this form, the polar form, is to give you an alternative way to multiply 2 complex numbers, to divide 2 complex numbers, and to take a complex number and raise it to a power. So we'll take a look at that, and that'll be the conclusion of what we're going to do today. So here is the multiplication rule. You can find this on page 729 of the textbook. We have a complex number z sub 1 given in polar form. It has a length of r sub 1 and an angle of theta sub 1. And z sub 2 is a different complex number. Its length is r sub 2. Its angle is theta sub 2. And what we have here as far as the product of these two numbers go is the formula works as such. We're actually going to take r sub 1 and r sub 2, and we're going to actually multiply those guys together. But the angles, we're going to take the cosine of theta sub 1 plus theta sub 2. And plus I times the sine of theta sub 1 and theta sub 2. So we'll take a look at an example of that here. So let's say we have one complex number, z1, is going to equal 4 times the cosine of 50 degrees plus plus I times the sine of 50 degrees. And we have another complex number, z sub 2, which is going to equal 7 times the cosine of 100 degrees, and I times the sine of 100 degrees as well. So we're going to do the product of these two numbers, z1 times z2. Our formula tells us that we can go ahead and we can multiply these numbers out in front. 4 times 7 is going to be 28. And inside of here, we're going to take the cosine of the sum of those two angles. So we're going to add those together. We're going to get 150 degrees. And there you have it. Depending on how they want you to leave your answer, if they want you to leave it as a polar form, you leave it just like that. And if the problem asks you to change it into rectangular form, you do what we did a couple of slides ago. Now with division, our quotients, excuse me, z1 divided by z2, using the same z1 and z2 as we had a couple of slides back. The rule, and this is on page 730, you can find it, we are going to take the two r values, r1 and r2, and we are going to divide those in that order. But this time, we're going to multiply by the cosine of the difference between the two angles. So we're going to take theta sub 1 minus theta sub 2. Then we're going to do plus I times the sine of theta sub 1 minus theta sub 2. And of course, we'll take a look at a quick example of that. So let's suppose we have a z1 of 12 times the cosine of 3 pi over 4, and I sine, 3 pi over 4. We have z sub 2, which is going to be 4 times the cosine of pi over 4, and I times the sine of pi over 4. So when we do our quotient, z1 divided by z2, what we're going to do in front is we're going to take 12 divided by 4. That's going to give me the number 3. Inside here, I'm going to take the cosine of 3 pi over 4 minus pi over 4. Thankfully, they're common denominators. I could quickly change that into 2 pi over 4, which is going to be pi over 2. So I'm going to have plus I sine of pi over 2. And once again, if they tell you to leave it in polar form, that is your quotient. If they ask you to change it into rectangular form, do what we did on the second or third slide. So the last thing here is raising a complex number to a power. And you'll find this rule in your textbook on page 731. It's called the Morse theorem. Here it is. We're taking z to the nth power. We're basically going to take r to the nth power. And on the inside, we're going to take the angle theta and multiply it times whatever power we're raising it to, so times n. And we have what we have here. So we will look at an example here. Let's suppose that we have z equal to, let's say we're going to take 2 times the cosine of 20 degrees plus I times sine of 20 degrees. And I'm going to take that number and calculate it being raised to the 6th power. So z to the 6th power here, what I'm going to do is I'm going to actually take the 2 to the 6th power times the cosine of 6 times that 20 degree angle. Well, 6 times 20 is going to give me 120 degrees. And I could leave it like that if it's instructing me to leave it in polar form. If I need to change, actually I take that back. We should probably at least call this 2 to the 6th power is 64 right there. But if it requires rectangular form, you would figure out what the cosine of 120 and the sine of 120 are, and you would go ahead and write that as rectangular form. Otherwise, you would leave it like this. So give this a shot. We're going to do a Math Excel assignment that will be posted for you.